Okay, in this video we're going to start section 3.7, related rates. In class we'll spend about 5 days on this section. Some of these problems can get a little involved, pretty complicated, and these are great problems for the AP test, especially the free response questions. So in this section we're just going to find related rates and use these related rates to solve some real-life type problems. But first, what are related rates? Before we read any of this, let's just look at the picture here. We have a cone, and the cone is full of water. If we look at the radius of the water, it's about that long. The height of the cone is here, and we could also measure the volume of the cone. Now we could pick any one of those three variables, the volume, the radius, or the height, and change it, and as we change each of them, they will affect the other two. I could change the height of the water level in the cone. Of course, that's going to affect the volume, and the radius at the top of the water level. I could change the volume. I could pump water out of the cone or into the cone, and the height of the water in the cone or the radius at the surface of the water will also change in relation to that volume. Or I could change the radius, which again is going to affect the other two. And these related rate problems are always tied together by time. So you've seen how the chain rule can be used to find dy dx implicitly. Another important use of the chain rule is to find rates of change of two or more related variables that are changing with respect to time. For example, when water is drained out of the conical tank, the volume v, the radius r, and the height h of the water level are all functions of time. Knowing that these variables are all related by this equation, our volume equals 1/3 pi r squared times h, we can differentiate implicitly with respect to t to obtain the related rate equation. So here's our original equation. We derive both sides with respect to t, and then we have here our from this equation, you can see that the rate of change of the volume, V, is related to the rates of both H and R. Here in our related rate equation, we have dH dt, the height with respect to time, and here is dr dt. As the volume changes, those are also in a state of change too. Here's just a real easy example. It's not tied into any type of real-life problem. They're just going to flat out give us the equation and a rate of change at a given point in time and ask us to find these two rates that are related. So we suppose x and y are both differentiable functions of time, t, and are related by this equation, y equals x squared plus 3. Find dy dt when x is equal to 1. Given that, they got to give us one of the rates at the start of the problem. Given that dx dt is 2 when x is 1. So we're looking at sort of a snapshot in time. When x is equal to 1, what else is going on with the rest of the problem? So the first thing I'm going to do here is copy our equation, and then we are going to derive with respect to t. So deriving the left side, the derivative of y is dy dt. And that's equal to, here's our x squared, we derive that and get 2x. And since we are deriving with respect to t, we have a dx dt created with the chain rule. And the 3 derives off into nothing. So here is our derived related rates equation. And now, we were talking about a snapshot in time. So when x equals 1, and when dx dt equals 2, those were given up here in the setup of the problem, we just plug those in. dy dt is what we're looking for. That's equal to 2x, or 2 times 1, times dx dt, times another 2. So 2 times 1 times 2 is 4. dy dt is equal to 4 when x is equal to 1. So here's some problem solving with related rates. In that previous example, you were given an equation that related the variables x and y, and were asked to find the rate of change of y when x is 1. So we had an equation that was given to us. We need a given rate. They told us dx dt was equal to 2 at this point in time, when x equals 1. They wanted us to find dy dt at that same point, when x equals 1. In each of the remaining examples in this section, we're going to have to create the mathematical model from a verbal description. Again, they gave us this equation, they handed it to us on a silver platter. We're going to have to work a little harder to come up with that equation. So, ripples in a pond. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown in the figure. We've got a pretty little picture here. So the pebble hits the water and the ripples emanate outward. The radius of the outer ripple is increasing at a rate of 1 foot per second. So when the pebble hits the pond, we hit right here. 1 second later, our radius is 1 foot. After 2 seconds, it's 2 feet. So our radius is growing at a constant rate. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? When we had a 1 foot radius, you know the area of that circle is pi r squared. So that would be pi times 1 squared, or just pi units. When we get out to 2, now the radius is going to be 4 times pi. As the radius gets bigger and bigger, every 1 foot increase in the radius creates a bigger and bigger, chunk of area that's added to what we had from before. So we want to find the area, the rate of change of the area of the disturbed water. So we need an equation, and I sort of already let that slip. We're talking here about the area of the water disturbed by this pebble hitting the pond. And if we remember back to geometry, or even probably before that, we have area equals pi r squared. We need a given rate. What did they give us that was given as a rate of change? I look at the paragraph that set up the problem, and I look for keywords, something like this, feet per second. That's a rate. What is changing at 1 foot per second? The radius. And, of course, seconds are a measure of time, so the radius, dr dt, the change in the radius with respect to time, dr dt, is equal to 1. And what are they asking us to find? The rate at which the total area of water, disturbed water, is changing. So we want to find dA dt. When what? When this, you remember these are like a snapshot in time. When the radius is 4 feet. When r equals 4. Okay. So we got the setup there. Let's see if we can solve the problem. Move this up here a little bit. So our formula, area equals pi r squared. Oops. Step 1, derive both sides with respect to time. So the derivative of the area is dA dt, and that's equal to, how do we derive this? Remember, pi is just a number. So by the constant multiple rule, we can just sort of bring that out front. The derivative of r squared is going to be 2r, and because we are deriving with respect to time, we have a dr dt. Okay, I think that's as far as we need to go. Now we can just start plugging in some stuff we have over here from the setup of the problem. So we're trying to find dA dt. And that stays as it is, and that's equal to pi times 2r. Well, what do we have? R is 4. So that's going to be 2 times 4, or 8. And dr dt, that was also given. Dr dt was 1. So we have pi times 8 times 1, or just 8 pi. And I guess since our radius was changing at 1 foot per second, this is 8 pi per second. So again, the pebble hits the pond when the radius is now 4, and here's our outer ripple. The radius is changing at 1 foot per second. How fast is all of this area changing? Well, 8 pi squared units per second. So here's 4-step guidelines for solving these related rate problems. Number 1, identify all given quantities and quantities to be determined. Make a sketch. A sketch can really clear things up. And then label all quantities. Now, step 2, write an equation involving the variables whose rates of change are either given or to be determined. Use the chain rule, implicitly differentiate both sides of the equation with respect to time, t. Remember, time is what relates these different rates. Step 4, after completing step 3, substitute into the resulting equation all known values for the variables and their rates of change. Solve for the required rate of change. Then a real important note here, I made this extra big in your notes. A real common mistake can be skipped if you follow this. When using these guidelines, be sure to perform step 3 before step 4. Substitute those known values of the variables. If you substitute them in before you differentiate, you're going to get an inappropriate derivative. You always derive both sides before you start substituting in your known values. Okay, this table below lists some examples of mathematical models involving rates of change. For instance, the rate of change in the first example is the velocity of a car. This just helps a little bit to take a verbal statement and pick out exactly what you need and, write it in terms of a mathematical model. So let's see here. In the first one, it says the velocity of a car after traveling for 1 hour is 50 miles per hour. So what did they give us? Well, first thing, they did give us a rate. And what is our rate? 50 miles per hour. So that's going to be d something dt, the derivative of something with respect to time. What are we going to use to stand for our variable here? Let's just fall back to good old x. dx dt is equal to 50. That's our miles per hour. That is a rate of change. And they also give us an initial condition. Remember, these are like a snapshot in time. When dx dt is equal to 50, when does that occur? Well, after traveling for 1 hour. So this is when t is equal to 1. When t equals 1. So we have a rate of change is equal to 50 at this point in time. So what does x stand for? If we have dx dt, what does the original x stand for? Well, that's just our distance traveled. Distance traveled. Oops, that looks like an R. It's supposed to be a V. Distance traveled. So x is our distance traveled. The rate of change in that, the derivative of x with respect to t, is 50 at this point in time, when t is 1. The second one, water is being pumped into a swimming pool at the rate of 10 cubic meters per hour. So what is our variable going to be? What are we talking about here? Cubic meters per hour. We're pumping stuff into a pool, a three-dimensional pool. So it's going to be volume, V. V is the volume of water in pool. Volume of H2O in pool. So did they give us a rate? Well, what's this? 10 cubic meters per hour. Well, what is that? Cubic meters per hour, we're changing what? The volume of water in the pool. dV dt. dV dt is 10 meters cubed per hour. Meters cubed per hour. And I guess on this one, they're not asking us anything else. They don't give us sort of a snapshot in time. This is a constant flow, 10 cubic meters per hour. And the last one, a gear is revolving at a rate of 25 revolutions per minute. So let's see here. A gear is revolving at a rate of 25 revolutions per minute. What is our variable going to be? And think about it here. We have, oops. Imagine this is a toothed gear. It's got teeth around it in industry. Those are terrible teeth. But it's meshing with another gear around it. So this is revolving at 25 revolutions per minute. And here's a little clue. 1 revolution is 2 pi radians. That should ring a little bell from pre-calc. So what are we talking about here? What is changing? What's our variable? Well, it's an angle. So let's use theta. Theta is our angle of revolution. And they do give us a rate of change. It's revolving at 25 revolutions per minute. So d theta dt, the change in that angle with respect to time, is going to be 2 pi. That's per revolution, and we're multiplying that by 25 revolutions. So that's going to be 50 pi rads a minute, radians per minute. And this might be, in some problems, this is going to be the hardest part, taking the verbal statement that you're given and turning it into a usable mathematical model. Let's squeeze one more example in this video, and then we'll stop for the next one. Example 3, we're inflating a balloon. So air is being pumped into a spherical balloon, see the figure, at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So imagine this, here in the small balloon, the radius is pretty short. Every pump is the same amount of increase in volume. Every time we pump, or every minute, we're putting another 4.5 cubic feet in. So in that first minute, 4.5 cubic feet will make the balloon go pretty big, and the radius will grow. As the balloon gets bigger, each minute it won't grow as fast because of the massive increase in the volume. So as it gets bigger and bigger, the growth of the radius will slow down. And we want to find out that instantaneous rate of change exactly when the radius is 2 feet. Oops. So let's see here. We got some stuff to figure out. What is our given rate? Given rate. Let's see, what is changing in the problem? Well, we're increasing the volume of the balloon by 4.5 cubic feet per minute. So we're talking volume here. That's going to be dV dt. The change in the volume with respect to time is going to be 4.5 cubic meters, 4.5, or I like fractions, I'm going to use 9/2. You can use 4.5 in your notes if you want. What are they asking us to find? Find the rate of change of the radius. So they're asking us to find dr dt. So we're looking for dr dt when, again, here is a snapshot in time, when what is equal to what? Well, when the radius is at a length of 2 feet, when r equals 2. And in the other examples, I don't know why it was put down here. In this one, the first thing we usually look at is what is the equation. Again, we're looking at a spherical balloon. That is a volume. Volume equals 4/3 pi r cubed. So there's our equation. Remember, the guidelines say take the derivative, and then we substitute in our known values. Don't plug that r is 2 in there right now or anything else. We want to take the derivative of this with respect to time. So dv dt, the derivative of the volume with respect to time. 4/3 is a constant. Pi is just a constant. We could multiply those right now and get 4 pi over 3, or even take it out to a decimal. So that's just a constant multiple there. But when we derive the r squared, that's going to be 2r dr dt. So here we still have r 4/3 pi, and then derive 2r dr dt by the chain rule. Whoa, back that up. Why didn't somebody stop me? I can't read my own writing. That is 4/3 pi r cubed. So I did not derive that correctly. Oops. So let's try this again. The derivative of v is still dv dt. When we derive here, this 3 is going to come down, and this will become a 12/3 pi, or 12 divided by 3 is 4. So that's going to be 4 pi. This r to the third becomes now an r squared, and then dr dt. There we go. So we're asked to find dr dt. We could solve this for dr dt right now, or as long as we've taken the derivative, we've derived implicitly, we can right now, if we wanted to, plug in those values. Let's see here. I'm going to make it a little harder. I'm going to divide both sides by this. I am going to solve for dr dt. Again, you don't have to. Dr dt is equal to, I'm going to divide both sides by this quantity, or dividing by that is the same as multiplying by its reciprocal. 1 over 4 pi r squared times dv dt. And now we can plug in our values that we do know. We are looking for dr dt. That is 1 over We still have our 4 pi. Now here's where the r comes in. This is our snapshot in time when r is 2. So that would be 2 squared or 4. And then times dv dt was given to us. That's 9/2. So let's see, here in this first fraction we have 4 pi times 4, or that's 1 over 16 pi times 9/2. And then what is that? If we just multiply straight across, I guess we can't reduce anywhere. We get 9 over 32 pi. And if we punch that into a calculator, find approximately, that's, pretty, we don't know exactly what that is, 9 divided by 32 pi. If we look at it roughly, it's 0.09 feet per minute. Feet per minute. So almost a tenth of a foot per minute for that spherical balloon. That's how much the radius is growing per minute as we continue to pump air into that balloon. I think there's a little wrap up to that example. Yeah, in example 3, note that the volume is increasing at a constant rate, but the radius is increasing at a variable rate. Just because two rates are related does not mean that they are proportional. In this particular case, the radius is growing more and more slowly as time increases. Do you see why? And we already sort of talked about that a little earlier. So this is a good place to end the video. We'll wrap up the rest of this section on related rates in the next one. Okay, example 4 here's a good one about the speed of an airplane being tracked by a radar. So an airplane is flying on a flight path that will take it directly over a radar tracking station as shown in the figure. So down here in the left corner is our radar tracking station. Here's an airplane flying in the direction of that radar station. And what does it say here? If S is decreasing at a rate of 400 miles per hour, when S equals 10, what is the speed of the plane? So it says here that this length here, S, is equal to 10, and S is decreasing at the rate of 400 miles per hour. So if we look here, the distance from the plane to the tracking station is x. The height of the airplane here is 6 miles, and this distance here, the distance between the radar dish and the airplane, that is decreasing as the plane gets closer and closer to the station. They're asking us to find the speed of the airplane just based on that information. So let's start filling out some of the relevant information we're going to need here. It might be easier to start with the given rate. What rate did they give us to start the problem? Well, S is decreasing at 400 miles per hour. So S is decreasing, so that's going to be our ds dt. And that's equal to, it's decreasing at 400 miles per hour. So are we going to put a 400 here? Or is it going to be a negative 400? It's got to be negative because that length is decreasing. So that's ds dt is negative 400 when, what is our snapshot in time here? When S equals 10 miles. S equals 10 miles. So they're asking us to find what? What is the speed of the plane? And if we look back to the picture here, here is our the flight path of the plane is along this side of the triangle. So we're using the x variable for the distance that it has traveled. And how do we measure speed? Well, that's going to be our dx dt. The change in x with respect to time is what we're looking for. And when are we going to, the speed is at this point in time also. If S is decreasing, when S equals 10, what is the speed of the plane? So we want dx dt also when S equals 10. And that's a little twist, and you're going to see why a little later in the problem. Or actually, we could do that part right now. If we look down here at the picture, we see a right triangle. So our snapshot in time says S is 10. So this is the hypotenuse is 10. This side here is 6 miles. That is written in stone. It's never going to change. They're not talking about the plane going up or down. They're just talking about it flying a straight path over that radar station. So if this side of the triangle 6 and the hypotenuse is 10, what is the side 8 or x going to be? It's a 3, 4, 5 triangle, and if we multiply our 3, 4, 5 by 2, we get a 6, 8, 10. So we want our snapshot in time here is when S is equal to 10, and also when x equals 8. When x equals 8. But remember, we do not want to plug any variable, any known quantity in until after we've derived, our raw equation. Oop, and let me drag that back up here. So what is the equation that we're dealing with here? Well, it's a right triangle, so it's going to be Pythagorean theorem. A squared plus b squared equals c squared, or in this case, x squared plus 6 squared equals s squared. Because s is our hypotenuse, we just square the other legs and add them up. And now we want to take the derivative of this with respect to time. So x squared, we derive and get 2x dx dt. The plus 6 squared, well, that's just 36. Derivative of a constant is 0. So this is equal to, the derivative of s squared is 2s ds dt. Okay, and what are we trying to find? We're trying to find dx dt, so let's divide both sides first by 2, so those 2's will cancel out. And then we divide both sides by x. So dx dt is equal to s divided by x times ds dt. So we've derived our equation. Now we can plug in our known values. We're trying to find dx dt. And that's equal to, well, s, we know that's equal to 10. X is equal to 8. So this s over x becomes 10/8 times ds dt, and that was also given as negative 400. So if you multiply that all out, you're going to get negative 500 miles per hour. So is that the answer? Is the speed of the airplane negative 500 miles per hour? No, that doesn't make any sense. The velocity is negative 500 miles per hour, but speed is equal to the absolute value of velocity. Velocity has direction. Because we're heading toward the station, the velocity is negative. If we were headed away, that velocity would be positive. But no matter what, if you take the absolute value of velocity, that is the speed of the airplane. That would be a nice little twist on an AP type question, or an AP type multiple choice or free response question. So here our speed is 500 miles per hour.